Okay, so now we're going to focus on some two variable gas relationships. For example, the relationship between pressure and volume when temperature is held constant. This is known as Boyle's law. So at a constant temperature, the pressure of a given amount of gas is inversely proportionate to its volume. What this means is that if you were to halve the volume, you're going to double the pressure. That's the inverse relationship. Now, why is this true? Pressure is caused by the collisions of the gas particles with the walls of the container. As that container volume is halved, those collisions become twice as frequent since there is less space for the particles to travel. And vice versa, if you were to double the volume, increasing the space for the particles to travel, you would then have the pressure because they would hit the walls of the container less frequently. Well, now let's look at this mathematically. So we have two graphs here. The first graph on the left shows volume on the x-axis and pressure on the y-axis. And this pattern or graph that we see is a clear example of an inverse relationship. And one major characteristics of inverse relationship graphs is they never actually reach the zero on the y-axis. And that's because as you increase the x-axis by some value, you decrease the y-axis by 1 over that value. For example, if I were to double the value of my volume, I would halve the value of my pressure. If I were to have 10x the value of my volume, I would be 1/10 the value of my pressure. This relationship gives us this continuous smooth curve that is very characteristic of an inverse relationship. But often the reason why we graph these values is so that we can define these variables with a linear equation. So for that, we need a line. And we can get a line by doing this second equation where we graph pressure on the y-axis still, but now the inverse of volume on the x-axis, 1 over volume. And we get this straight line, which is going to be equal to a y equals mx plus b linear model, right? Where y is the value of the pressure, x is the value of 1 over volume, b is our origin, which goes to the 0, and then m is the slope of the line. And since that slope does not change, that is a constant value, which we're going to call k. So that means pressure is equal to 1 over volume times some constant of proportionality, which we call k. A quick little rearrangement of this equation, and we can see that pressure times volume equals this constant K. And what this equation says is that if we take the pressure at any time and multiply it by its volume at that time, it will equal this constant value K. And this is huge because now this allows us to connect two different times together. Since at time 1, the product of P and V equals K, and at time 2, the product of P and V also equals K, that means the product of P and V at time 1 are equal to the product of P and V at time 2. And this here is Boyle's law, where P1 times V1 equals P2 times V2. Now, let's see if you can apply this equation for this practice problem below. Pause the video and I'll be back in a moment to show you the answer. Okay, so in this problem, a diver blows a 0.75 liter air bubble, that's our initial volume, V1, several feet underwater. As it rises to the surface, the pressure goes from 2.25 atm, that's our P1, to 1.03 atm, that's our P2. What will be the new volume? So we're trying to find our V2. So we can actually rewrite Boyle's law equation into V2 is equal to P1 times V1 over P2. And now this will allow us to input our values and solve. Since I have pressure in the numerator and denominator, the units atmosphere cancel out, and my answer to 2 sig figs is 1.6 liters. So now we're going to look at the relationship between volume and temperature when we have constant pressure, and this is called Charles' law. The volume of a given gas is going to be directly proportionate to the absolute temperature of the gas when pressure is being held constant. Now, how do we have a chamber with constant pressure? Well, we use a thing called a piston, a movable piston. And this piston has a weight on it where the same amount of force is being applied to this piston at all times, hence the constant pressure, but the volume can expand as need be. Now, why does this work? Well, if you heat a sample of gas, the gas particles begin to move faster. As they begin to move faster, they start to collide with the walls more frequently, causing the piston to move outward and the volume to expand. Just like with Boyle's law, we're going to define this mathematically. But when you plot the data for temperature and volume, we already see that this is a linear relationship. So this means that volume, our y value, is equal to that constant slope times temperature, our x value. Not 1 over temperature like in Boyle's law, but temperature itself. Just like with Boyle's law, we can rearrange this to equal K, but this time we see that volume divided by temperature is equal to that constant of proportionality K. And this makes sense because volume and temperature are directly proportionate. So if I increase volume, I also have to increase temperature to have it equal to that constant of proportionality. And if I were to decrease volume, I would also have to decrease temperature to still be equal to that same constant value. Just like with Boyle's law, this allows us to take volume and temperature at time 1 and relate it to volume and temperature at time 2, where V1 over T1 is equal to V2 over T2, because at time 1, V1 over T1 is equal to K, and at time 2, V2 over T2 is equal to K, so the two are equal to each other. And this equation here is Charles' law. Now try to apply it on the practice problem below, and I'll be back in a second to show you the answer. So in this problem, we have a 2.2-liter balloon that is going to be heated from 22 degrees Celsius to 71 degrees Celsius. Now we know that temperature and volume are directly proportionate, but we need to focus on the fact that they're directly proportionate when you're looking at absolute temperature, not Celsius. So we're going to convert both these temperature values into Kelvin by adding 273.15. Once we do that, then we're going to rearrange this equation so we have V2 equals T2 times V1 over T1. Allows us to input our values and solve. The unit Kelvin cancels out in the numerator and the denominator, leaving us just in the units of liters, and our answer is 2.57 liters. Well, now let's talk about the relationship between pressure and temperature when you have a constant volume. Pressure is directly proportional to the absolute temperature of a gas, while volume is being held constant. And this probably makes sense. As you heat a gas, you increase the average kinetic energy, causing the gas particles to move faster. Faster moving particles will collide with the walls of the container more frequently, and when they collide, they'll actually have greater impact force. So the combined effect of more collisions and stronger collisions results in pressure going up. And if volume is going to be held constant because you're in a rigid container that can't expand, well, then pressure is going to go up very, very fast. And just like when we talked about volume and temperature and their direct relationship, pressure and temperature direct relationship can be defined mathematically as well. And since it's the exact same relationship as volume and temperature, we're just going to write the equation here. We know that pressure is equal to temperature times some constant K. We rearrange this, we get pressure over temperature equals that constant of proportionality K. Now, once again, since we know it's directly proportionate, that allows us to rearrange this equation to be that pressure over temperature is equal to that constant of proportionality K. And if at time 1, pressure over temperature equals K, and at time 2, pressure over temperature equals K, well, then we know that pressure over temperature at time 1 is equal to pressure over temperature at time 2. And again, this is the Gay-lussac law, the relationship between pressure and temperature at a constant volume. Now let's try to apply it. Try this problem down below, and I'll be back in a moment to show you the solution. So in this problem, we're trying to find the new pressure of an aerosol can that started off at 45 psi of pressure at an initial temperature of 25 degrees Celsius. And if we heat that can up to 650 degrees Celsius, what will that new pressure be? Well, again, just like before, these values are proportional to temperature when temperature is in an absolute scale. So we have to convert both of these temperatures into Kelvin. And we do that by adding 273.15 to each of the temperatures in Celsius. Since we're solving for pressure 2, we can do a quick little rearrangement of the equation, and we'll get P2 is equal to T2 times P1 over T1. We then could just input our values and solve for the problem. And we find that the pressure at time 2 is 140 psi. And our final two variable law is when we look at the relationship between the volume of a gas and moles of gas particles present in that gas when you have a constant pressure and temperature. And this one's pretty easy to guess what's going to be the relationship. Volume of a gas is directly proportionate to the number of gas particles in moles present. When you increase the amount of gas present, you have more particles colliding with the container. If you're going to have a constant pressure and constant temperature, well, then the volume of that chamber must expand. And again, you need a movable piston or a balloon that can expand in order to see this, but this is a pretty obvious relationship. As we've already seen in the last two direct proportional relationships, we can represent this mathematically as the volume divided by moles, which is N, is equal to some constant of proportionality. And since the volume at time 1 divided by moles at time 1 is equal to that constant, and the volume at time 2 divided by the moles at time 2 is also equal to that constant, then we can set these two equal to each other, where volume at time 1 divided by the moles present at time 1 will be equal to the volume at time 2 divided by the moles present at time 2. And this is known as Avogadro's law, based off of the same person that came up with Avogadro's number, the number of particles in a mole of a substance, 6.02 times 10 to the 23rd. Just with the last couple of laws, try this one out, and I'll be back in a moment to show you the solution. So if we see here, we have a volume of a balloon that has 1.50 liters, and it contains 0.0920 mole of helium gas. Now we're going to add 0.0210 mole of additional helium, and we want to know what is the new volume. So we clearly have our V1 and N1, but that's not quite our N2. That's additional moles added, so we have to add that number to our initial moles to find our N2. Then we're going to write down Avogadro's law. V1 over N1 is equal to V2 over N2. And since we're solving for V2, we're just going to quickly change it into a form that's going to be V2 is equal to N2 times V1 over N1. We will input our values and then we'll solve for volume 2, which is equal to 2.33 liters. Okay, so Avogadro's law tells us that volume and moles are directly proportionate, but their exact relationship depends on the values that you hold constant for the temperature and the pressure. Well, STP is one specific set of pressure and temperature values you can hold constant. When you're at STP, your temperature is set to 273.15 Kelvin and the pressure is 1 atm. And it turns out that when you're at STP, the specific set of values that you hold temperature and pressure constant at, well, the 1 mole of gas, any gas, will occupy 22.4 liters of volume. This conversion is known as the molar volume, but it is only true when you are at STP. So again, at STP, 27.15 Kelvin and 1 atm of pressure. We just went through four different gas laws. Boyle's law, where pressure times volume equals some constant of proportionality. Charles' law, where volume divided by temperature is equal to some constant of proportionality. Gay-lussac law, where pressure divided by temperature is equal to some constant of proportionality. And Avogadro's law, where volume divided by moles is equal to some constant of proportionality. And it turns out that since all these laws are all related to each other, we can make one law out of them called the combined gas law, where if you know the pressure of the gas times the volume of the gas over the moles of the gas and the temperature of the gas, that is all equal to a constant of proportionality. And this is called the combined gas law. And therefore, we can take that and know that P1 times V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. And memorizing this law is super helpful because you can get to all the other laws from it. If anything is held constant, you just eliminate it from this equation. And then you can get to Boyle's law or Charles' law or Gay-Lussac's law or Avogadro's law. Okay, try this combined gas law problem below, and I'll be back in a moment with the solution. Okay, so in this problem, we're told that the initial volume of this weather balloon is 3.2 liters. We know the initial temperature when it's launched is 25 degrees Celsius, and that it's at a pressure of 100.0 kilopascals. When it's released, it's going to go really high into the altitude, and that pressure up there is only 475 pascals. Don't be tricked by the fact that this number seems larger. Pascals is a smaller unit than kilopascals. The temperature up there is very cold, -50 degrees Celsius, and we want to know what the new volume is. Since we have so much information, I think it's very useful to just organize all of our information in the problem in a little table. We have our pressure values, we have our volume values, our mole values, and our temperature values. Now, it doesn't say anything about moles in this problem. And since it's a balloon, probably the moles isn't changing. So we're going to assume that this value is constant. And since it's constant, we're not going to include that variable in our equation. We're just going to simply eliminate it from the combined gas law equation. So that means the equation we're going to start with is P1 times V1 over T1 is equal to P2 times V2 over T2. Since moles are being held constant, we do not include it in our equation. Now our pressures have to be in the same unit, so I'm going to convert pascals into kilopascals by dividing by 1,000, since 1,000 pascals are 1 kilopascal. And then lastly, I'm going to add 273.15 to both of these temperatures to make sure that they're in Kelvin because I need absolute temperature scale for any of these problems. Since I'm trying to solve for volume 2, I'm just going to multiply both sides by T2 over P2 to get V2 all by itself and move those variables to the other side of the equation. Now I can just input all my values and get my answer for V2, which is 504 liters. Try these on your own and then check the answer key on the class website.